All right, everyone. My name is Margaret Marr, and I'm a master's thesis in the HGN lab for bionic engineering. Thanks, everyone who came today. And today I'm going to be talking about a paper out of Aaron Young's lab out of Georgia Tech. And the name of the paper is Comparing Metabolic Costs and Muscle Activation for Knee and Back Exoskeletons in Lifting. A little bit of a mouthful. So first, brief overview of just what exoskeletons are. I really like this definition. Exoskeletons are wearable structures that support and assist movement to augment the capabilities or to assist movement or augment the capabilities of the human body. And I just put a couple examples up here on the slide. So in square one, we can see like this is very rehab focused. This is a very big device. It's very clunky. It's doing most of the work for the person. In square two, kind of more of a research device. And then kind of 3 through 6 are devices that are designed with the intent to be used in an occupational setting. So we see a shoulder exoskeleton to kind of help with fatigue in the upper extremities. And then this bottom row is all lifting and then trunk support exoskeletons. So exoskeletons have, multiple different applications and uses. And the two kind of big buckets you can put exoskeletons in are passive versus active exoskeletons. And so a passive exoskeleton is an exoskeleton that relies on using things with elastic properties, springs, dampers, elastic materials to provide torque. So you can think of when you have a rubber band, if you take that rubber band, you stretch it out. As you increase that distance, you're increasing the force, trying to bring your hands back together. And so passive exoskeletons are typically relying on some sort of physical deformation to provide a uniform distribution of torque. A active exoskeleton is going to be an exoskeleton with motors, batteries, actuators, and it's able to actually interject energy into the system or add power into what's going on. And I think that these two plots from the paper highlight these differences even better. So you can see in figure B, we have the passive exoskeleton used in the study. Along the x-axis, they have percent lifting cycle. You can just think of that as a squat. This is 0%, 50%, 0%. And as you can see, the torque assistance of that passive exoskeleton is directly related to the deformation, or in this case, the peak knee flexion that's occurring during that squat motion, right? So at the beginning of the squat, you don't get very much torque. At the end of the squat, you get a lot of torque, and you get the most torque when you have the biggest knee flexion. If you look at figure A, what we see is you want to look at this orange line. This orange line is not correlated necessarily with that purple line, which is knee flexion throughout the movement. And so what I'm just trying to highlight here is that with a powered exoskeleton, we're able to augment and adapt where we want to add power throughout the time series here. And it's not necessarily directly dependent on how much knee flexion you have or deformation you have in the system. Okay, hopefully everyone is still following. I know that's a little bit of background here, but in this study, they wanted to compare a powered knee exoskeleton and a passive back exoskeleton. So not exactly apples to apples, but I think it's a fair comparison, and we'll kind of get into that later. And the primary outcomes is they wanted to do a metabolic comparison as well as a EMG or muscle activation comparison. And then some secondary outcomes there were just perceived exertion, comfort, and preference. In this study, they recruited 10 subjects, and they had 2 females, 8 males, and everyone was about the same size, about the same weight, about the same age. And that's because I can almost guarantee that they were grad students in the lab. That's just how it shakes out sometimes. You got to use what you have available to you. So there wasn't a great diversity in the subjects. And in this study, they had people lift a 25-pound kettlebell from a set height, which was about waist height to about knee height. It was like here to here. And they collected their data over 2 days. Day 1, they collected their metabolic data. When you collect metabolics, you use what we call a K5 COSMED system. And you have a mask and you wear a little backpack, and it's a little cumbersome to use with other systems like EMG. So I wasn't surprised. In fact, if I'd probably done the study, I would have done the same thing. I would have collected data over 2 separate days. So on day 1, they did 6 minutes of lifting. And then on day 2, when they collected that EMG data, they actually broke the lifting into distinct lifts and lowering motions, which was a little bit of an interesting take. And maybe not exactly what I would have done, but for day 1, for that 6 minutes, it was just 6 minutes of continuous lifting at a set cadence. And on day 2, they also collected some of that perceived comfort, helpfulness scores on the exoskeletons, or throughout all these conditions. this is a really cool graph that they made. When they were trying to decide how much assistance they wanted to give with that powered exoskeleton, you have something which you might call your controller, and you want to maybe normalize that to someone's body weight or how someone may move or their height, something like that. And so they did all this work where they had some people come in for pilots and they normalized their EMGs for the stiffness and damping. But the most important thing about this plot is that it didn't actually matter because they did all this work and they found out that this kind of middle point here, that just represents the max capabilities of the exoskeleton. And so they found that everyone had the best result when they gave everyone basically the max amount of stiffness or assistance, which is not totally shocking. And so they chose to give everyone the same amount of assistance. But this is really great, and it's a really great justification as to why they did that. And this is actually something I might try to put in one of my papers because I think it's pretty cool. Next here, they also gave us a little diagram of which EMGs they chose to use. For those of you that don't do EMG studies, this study had 16 EMGs. That is a ton of EMGs. That's a lot of prep. That's a lot of placement work. And so kudos to them for doing all of that. And they had these EMGs both on the trunk, back, and then as well as the lower extremities on the legs to kind of capture both the back, the targeted muscles in the back and the targeted muscles in the surrounding the knee. All right, so the major result, or the kind of like the biggest takeaway you could say, is that the knee exoskeleton had, they found that it reduced the metabolic cost of the task, which was lifting and lowering this 25-pound kettlebell by around, let's call it 10%. And that was statistically significant from the no exo condition and from the back exo condition. So the back exo did not reduce the metabolic cost of this action, but the knee exo did. They also collected some perceived exertion scores, and we see that the knee exoskeleton, when people were using it, they perceived the task to be easier, and that again was statistically significant, and it was not statistically significant between the no exo and back exo condition or the back exo to knee exo condition. That last bar chart is a pain scale. They collected pain ratings, but they were all super negligible, so didn't end up being a significant result, but I think it's nice to capture anyway. Now, this is a little bit where the story gets a little bit muddled because they had this helpfulness rating, and although the back exoskeleton didn't necessarily reduce metabolic cost, people still rated it as very helpful. Furthermore, they didn't rate the knee exoskeleton as being more helpful than the back exoskeleton to a statistically significant matter. So this is kind of an interesting finding, and I think possibly that this wasn't maybe the best scoring tool they could have used. And we kind of see this again in the exo preference rating. People did overwhelmingly like the knee exoskeleton, but they also did like the back exoskeleton, although the back exoskeleton didn't reduce metabolic cost. And moving on to the EMG results, this is a very big plot. It tells you a lot of things about what all the muscles are doing. And basically, they're just comparing and contrasting to the no exo condition, what muscles were maybe activated more and what muscles were activated less. I've kind of just broken up the findings of this plot into 4 main points for you guys. And the first of which is that each exoskeleton did have a positive effect on the target muscle group, meaning that the powered knee exoskeleton helped to reduce muscle activation in the legs, and the passive back exoskeleton helped to reduce muscle activation in the back. That's great. It's kind of what you would expect. They also saw that the exoskeletons had marginal positive effects on surrounding muscle groups, which is kind of in line with some other findings, but it wasn't statistically significant, and you're not totally sure exactly why that happens. Unfortunately, the passive back exoskeleton did have a significant increase in certain muscle group activations, which wasn't what the authors were expecting to see, and is kind of in line with this last conclusion, which is that the authors with these findings, were unable to make a direct correlation between muscle activation or a decrease in muscle activation and decreased metabolic cost. And one of the reasons they give for that is because during this kind of motion, the back muscles are not doing a lot of what we call positive mechanical work. And positive mechanical work is very metabolically expensive, you could say. But in contrast, the leg muscles are doing a lot of positive mechanical work. So possibly there just wasn't that much room for improvement in reducing the muscle activation into translating into reduced metabolic cost while using a passive back exoskeleton versus with the powered knee exoskeleton that reduced EMG activity. There was more room to grow in terms of reducing the metabolic cost of the activity. And I think my kind of favorite line from the study is that the fact that the back exoskeleton was more preferable than the no exo condition, which go back and look at that pie chart, which you'll see, despite not lowering the metabolic cost, indicates that user preference is made up of factors other than just exertion. And I think this kind of hits the nail right on the head in terms of the research that we do. You can tell someone every day of the week that this exoskeleton is going to reduce your muscle fatigue. It's going to make it easier for you to do these lifts and complete these activities. But user preference is probably multifactorial and may not be something that, while we can measure scientifically, is really going to be captured in our research, but is really important for any sort of future adoption that may or may not happen with this kind of technology. And so I really appreciated the authors taking some time to try to capture some of these metrics and also comment on them as well. Because it's really easy to say, like, everyone's going to want to use my device. It made it easier to lift, right? You can say that, but if you're trying to capture people's preference and opinions, that's a little bit different. So some strengths and weaknesses. I'll start with the strengths. I liked that they collected both quantitative and qualitative data. If you flipping through kind of their methods for collecting the EMGs as well as their metabolics, gets the okay for me. I thought their methods were fine, how they sampled things, how they chose to place the sensors. I thought that was totally cool. I really liked their justification for how much assistance they gave people. It's pretty common in these kinds of studies for like I'd be the grad student being like, Grace should get 5 newtons and Bubba should get like 12 newtons, right? And it's a little bit subjective. So I liked this justification for how much support they gave people in the powered exo condition. And then I also appreciated that they didn't overdo their statistics, but they did some corrections, which I would have, liked to see. They did the one-way ANOVA. They did the Bonafide correction. So I appreciated that. And then some of the weaknesses in this study were that the diversity of subjects, like, you just can't get grad students. It's who you have in your lab. You don't have a lot of choice. And then they changed the study protocol between day 1 and day 2. So in day 1, they did a continuous lift and lower. In day 2, they just lifted and then they would just lower. And I didn't quite understand why they did that. And I think it was not super helpful for their EMG results, but I suspect they did that because it may have been difficult to sync between different systems. So it was probably easier to slice the lifting and lowering motion that way by having people only lift or only lower. And I think the helpfulness scale, they cited a paper where the scale was used before, but it was used in a really different context for like neurological back pain. And so I don't think it was overly applicable to exoskeletons. And I think that's also possibly why the result on the helpfulness scale was not great and maybe actually a little bit misleading. And then lastly, the exact torque profile that they used was still a little ambiguous. If you look at the caption under figure 1, it kind of says, well, this is like a sample of the torque profile. And it was very unclear if that torque profile was for the day 1 or day 2 data collections. And one of the reasons I suspect that maybe it's not the exact one is because at max knee flexion, they're not getting any torque, which I would not expect to get a positive result from that, but I could be wrong. So I would have liked if they had shown the exact torque profiles that they provided to the subjects in the study. Yeah, I've just got a couple discussion questions, but I'll open up the floor to anyone who's got any comments or questions. Good.
So I like that they actually tried to look at preference a little bit, because what typically happens is an engineer or an engineering team or development team develops something, and then they hand it to the marketing team, and the sales team's like, all right, go sell it, right? And there's not a whole lot of, in many cases, not enough dialogue between the two about what does the end user actually want, what does the end user prefer, kind of thing. But there is a whole science to that, right? They do it, but they're all doing it over here, and engineering and development is over here, and like I said, they don't talk very much. So it was nice to see that they were acknowledging that.
Yeah, I don't think their execution was particularly good, but I did like that they acknowledged it.
Yeah. So I guess the question for you or for the group is, how would how would they or would someone who's doing this kind of development process, how would they include, or what would be the right way to include some sort of, preference or analysis of that aspect of this be done? How would that be done?
Yeah, so actually, before I came back to school, I actually did quite a bit of that. I worked for an exoskeleton company, and we did a lot of preference testing. And I'm not going to say we did a great job, but a couple different. Typically, we like to take people like out of out of the environment, out of the exoskeleton, because unfortunately, I think when you're asking someone to do a hard task, like lift something, even with an exoskeleton, the task tends to suck, right? So people are like, I don't know, this was still really hard, right? And this improvement is maybe not as much as I wanted it to be. And it's pretty hard for people to capture that 20 to 30%. So I think one, letting people have more time with with this kind of technology to give you a little bit better feedback. But then also there are more standardized surveys that you can give that they did not give in this one. One of which is like I think it's called the NASA survey. It's about like pain and discomfort. And I think I would have liked to see one of those as opposed to this helpfulness and this kind of preferential ranking.
There are also only 10 people, so an interview with each person about their experiences with each bit of equipment could reveal a lot about why preferences went one way or another. So
Yeah.
open-ended interview questions with a small sample can help you out quite a bit.
Totally. And I think one of the weaknesses I didn't point out is, again, because they're just using grad students, your friends probably like you. Your friends probably don't want to go on record as being like, oh, that exoskeleton you made really wasn't that great. And so these people not only were probably a little bit biased, but they also were probably, if you're in this kind of research, you're typically wearing these devices a lot. So I would have considered all of these people to be more of like an expert user type case. So these are probably better results than you would see with like the average person in this room.
Oh, sorry.
Wonder if also you could give them like some placebo type cases where you say you're going to give them this assistance, but you don't, or you give them less and see how the
Yes.
preference changes as well.
Yeah, you do see that in some studies where people will do like a no assist case, which is fairly interesting. I don't believe they did one in the study, but
So I was wondering about whether or not they assessed lifting technique, because bending at the waist is metabolically much less costly than bending at the knees. Bending with your knees and activating the quads. So did they measure or assess lifting technique?
they didn't necessarily, they did measure it in that they did capture. So with these EMGs, you also get IMU data. And so they were able to look at, I think this is in the supplementals, they were able to look at trunk lean, and there wasn't necessarily a big change, but they didn't like score or grade it. They did mention that most people chose to use like a hybrid like stoop lift motion, which in more recent literature is showing to actually alleviate low back pain. And I think one of the driving factors is that my understanding is that there's a lot of it is based on anatomy. And so people tend to lift in a position that is less stressful on them. And so it can be, you can sometimes make your results worse if you ask people to lift in a very particular manner. Although like in this case, if you're using a knee exoskeleton and you don't bend your legs, it's like not going to help you. So
Then I also thought that the weight of the back exoskeleton, I don't know if it was substantial or not, but that might
no.
have played a factor in.
Yeah, I think the HeroWear probably that's the passive back exoskeleton they use. It's really just like resistance bands that you strap on. It's super light. And I will say that they put a load cell in between those bands to make sure that everyone was getting the same amount of assistance. And they even went down to make sure that like when they put the load cell in, that made the band like a little bit smaller, and they like compensated for that as well. So I think they did a good job controlling for that.
About the way they constrained the height of the lift with this little shelf.
I think if I was the researcher, I would have done the same thing because it's nice when everyone does the same thing. And also, if you looked at the people that they had, again, everyone was kind of the same. So you didn't have you didn't have some guy who was like 6'8" being like, this is still below my knees. I think it was smart, but it was also extremely arbitrary. Like they didn't have a great justification, or like this is the average height of an Amazon shelf, or like this is the average height of a lift of this warehouse worker. It was pretty arbitrary, so
Scale to the subject height.
no, because the subjects were all basically the same. So kind like pseudo, yes, but not really. I said I talked too fast during my presentation. I probably didn't take enough. Yeah, Andy.
So this might kind of lead into what I'm going to talk about.
Oh, that's perfect.
So like your paper is really going into like EMGs, metabolic costs, and all these kinds of results, but it doesn't really try and estimate like any of the amount of like force or torque that's on the lower back that might be
Sure.
really important to look at for like a lifting task. And I guess like how would you interpret like EMG and like muscle reading off of the back as far as like do you think that you can like relate it to like your what's happening at your like your lumbar?
Yeah, so I think there's a couple researchers that are attempting to do this, and there's a couple challenges in that most of the time when we want to look at like the things that may be happening physically, like the compression in the low back, you do it with like a cadaver. You don't do it with a living person. And so you're trying to capture these kind of internal metrics on someone that's, mind you, already wearing a bilateral exoskeleton, right? So they're wearing one on each leg. They also have 16 EMGs. There's a lot going on in these data collections. I think it's hard. One of the ways we could go about this, which is a subtle plug for my current research, is to do biomechanics studies where you do a similar task and then you put on like markers, and then we have special cameras that look at those markers, and then we put it into two special programs that do a bunch of math, and then it will back calculate the joint torques. And through that, we can create a segment at the low back to try to understand how much torque is happening there. But in terms of the actual spinal compression, I think that that's something that the research is still trying to figure out how we can take a biomechanics study like that and relate it to back compression in living people, although we can probably make some smart assumptions, like the larger the torque at the low back, maybe the higher risk for low back pain or injury, although there's not a very clear correlation, and we don't have enough research to support that hypothesis at this
Yeah,
time.
like did they do kinematics in this at all?
They did a little bit. So the EMGs had an IMU, and I think they had a separate IMU on the chest as well. So they did look at trunk lean. Again, I do think that's in the supplementals, although I'm not totally sure, but it wasn't totally different. And I don't think they didn't do any kinematics in the passive condition. I think the kinematics they got in the powered condition came from the IMUs that were in the robot.
Yeah, because like from like reading papers and stuff from what I was looking at for this week, they go into a lot of depth on like, oh, you're using this back exo, but if your kinematics are different without using the back exo, then like what can you really say about like your study? You're doing it
Yeah.
differently.
And I think
So
for this, that's why I would have preferred to see a no assist condition or a transparent mode condition, which is not really possible with the passive exo. But for the powered, it would have been nice to see kind of if you looked at the kinematics for a kind of slick condition, so you're not wearing the exoskeleton, and you want to compare that to the condition where you're wearing the exoskeleton, but you're not giving any power, which usually they do change a little bit, right? By wearing something, you stand a little bit different. And then also comparing that to the powered condition, because it may be really easy to say like, oh, well, we were really helpful between this, no exo condition and this powered condition. But if all your powered conditions are actually just worse than your no exo condition, or the no exo, no assist, then not really helping.
yeah, like another big part is just I guess like from my paper, they say like the relationship between EMGs and lumbar moment is nonlinear. So you can't just assume, oh, my EMG is going down. So I should have like less stress on my back. Like that's not necessarily the fact. And there's a ton of muscles in your back too. And with EMGs, you can only measure the surface. when much deeper, like in our bodies, there's these other muscles that are doing a lot more.
Yeah, that's a really good point. And I think if you're not super familiar with collecting EMGs on the back can be a little bit tricky because those muscles tend to be, like Andy said, you're collecting on the surface level, and sometimes they're only exposed on the surface level in a very small area. So you're trying to get, the placement is very important, and it would be pretty easy to maybe not put the EMG totally in the right spot or not get a great reading off of it. So I think that's another good point that Andy brings up, as well as what we talked about earlier with that positive mechanical work. Those muscles just aren't doing a lot of it. So, the strain necessarily that's happening there, like Andy said, isn't necessarily linear. Anything else?
Anything else for Margaret? Going once, going twice. All right.
How do you, Andy? Way to tee yourself up.
I made it.
I talked really fast and it's done like 12 minutes. The demo's really good. I have like enough.
Okay. Okay, so good job, Margaret. You did a good job. Now I'm going to kind of go into why EMGs and like all these other results are like really hard to kind of like replicate, and how like some other assessment tools might be better for like companies to kind of evaluate using a back exoskeleton for their company. So that's kind of like what this study tried to do. So like Margaret kind of already said, like 40% of these like disorders are related to the lower back. So a lot of companies see a lot of issues with like missed time, and a lot of money is like lost due to all these injuries for companies. So as like a ergonomics and safety student, kind of like an ideal job would be to work for a company to like limit these injuries for the company and try and mitigate it so they can work maybe more efficiently and not get injured as often. And there's been plenty of like these rules that we kind of learn in our classes that we're taking here in the ergonomics class for what they might do, like the rula and like different lifting tasks. But there hasn't been a mapping for how much an exoskeleton may reduce like damage to tissues and cause like these overexertion injuries that relate to back injury risk. They kind of went into the paper and brought up how it's been done for the shoulder, but not necessarily for the back. And they basically, I think that they said Toyota was able to, hold on, let me find it. They said that after a few years of exo use, Toyota has now reported lower medical costs and fewer injuries in job roles using shoulder exoskeletons. So kind of the motivation is to kind of try and bring that to use for back exos. So they're basically trying to come up with a tool that they can use to assess back injury risk while using a back exoskeleton. So we kind of saw some of these devices already from Margaret's study. This one, B in particular, is the same one that they used in the other study. And it's a passive soft exo, so it's just using like these bands on the back that you can replace with different strengths and like stiffnesses, which I'll kind of go into more later. And then in the middle region, also you kind of saw before, like more rigid components. And off to the far right are like fully powered robotic exoskeletons, which we develop in our lab, which is really cool. But we'll just be focusing on B for the rest of this. So we might have seen this like before in like our ergonomics class, but they're using this lift assessment tool, the lifting fatigue failure tool. And it's basically taking the component of how heavy is your thing that you're carrying, how far out in front of you are you carrying it, and how many repetitions per day are you doing like this task. And then it's coming up with this like development of like your cumulative damage to your tissues and like your lumbar support in your back. And then they give you a probability of the job being high risk. So they did a comparison of the lift equation, which has been like simplified. And you can see on the like the top right, it's MPL is like your moment of your peak lumbar moment while lifting. So they're basically adding up all those times that you're lifting throughout the day and coming up with this damage tool. And what this paper basically did was saying, okay, if I need to figure out like my biological peak moment, I'm just going to subtract what the exoskeleton does. So you kind of think, okay, that seems like pretty simple. It seems like just by subtracting like this moment from the exoskeleton, obviously it would make things like way easier. And that's kind of what they found. So in this like first result, it's just a simple prediction just by putting in all these values for different object weights, and they use different strengths of the bands, like 35, 25, 15, and they just plugged it in and they calculated this like percentage change basically from no exo to exo. They found this huge reduction, and it's like, wow, this is so amazing. It seems really obvious. So they went into and did a second result or a second test that simulated all these different work days. So they basically said, okay, well, you can carry like a variety of mixed objects. So they added in like 2 to 8 kilograms, 2 to 22 kilograms, 16 to 22 kilograms is all the heavy objects. And they added in different assistance amounts for the exoskeleton. And they also added in like different lengths away from the body and that sort of stuff. And they randomly like got all these different like 1,000 simulated work days, and they basically see there's still a reduction, basically just coming from like this exo assistance that they're subtracting from this equation. So going on to the next result is more of a ergonomic assessment on an actual worker. So for this person in particular, they had wear the exoskeleton and they videotaped them throughout their shift. They saw they did like 200 something lifts on camera. So they were kind of able to estimate, okay, I can see the box is this heavy based on its like postage or whatever. And just by like visually inspecting it, they could see, okay, it seems like it's this far away from the body, and all those sorts of different measurements. And then they found that there's this huge reduction again. They tried 2 different band types, 23 and 30 Newton meters. worth of like lumbar support moment when they're bending over to pick it up. And then their low back risk also decreased. So it seems like from like their simple result on the first one is like 68%, 21%, 58%, 18%. And then they're getting like these same values of reduction by doing it on this person that was at work. So it's kind of interesting that they were able to kind of compare like their simple model and get relatively similar assessments of damage and lower back risk. So for my AI portion of this, I said, okay, give me like a cover photo of this study. And I thought it was really cool. They gave me like this really cool exoskeleton on the back. There's this graph on the top right that seems like it's increasing risk while wearing a back exoskeleton. I was like, well, that doesn't seem right. And then there's this like bright shining light in the middle. And I asked it, what is the light for? It's like the glowing overlay on the lower back symbolizes the exoskeleton's support and functionality. So in conclusion, this paper kind of concluded that they think this ExoLift assessment tool is pretty informative, and it could potentially help like these safety professionals explore more into back exos as being part of their programs. And they saw that the reductions in both risk and damage were very similar. So yeah, I'd like to go into maybe some questions for you guys now. But I guess like the main question I'd like to ask is, do you think this assessment tool is like good enough, or is there any limitations that you might think to like this tool? Yeah, Kai.
I kind of have a fundamental question, which will influence my answer, but was the exoskeleton theoretically the peak moment of the exoskeleton and the peak moment of the biological joint, were they aligned? Because they're doing a one-to-one subtraction. So biomechanically, to get the biological torque, the peaks of the moments would have to be aligned in time.
Yeah, they're assuming this perfect subtraction, right? So kind of what I was getting into earlier with Margaret was, okay, like what is like the timing of like this said exoskeleton? And it's like a passive device, so that's also kind of hard to figure out when it's like applying this amount of torque to the body.
Right.
So I think that is like one of the major limitations of this.
Main concern.
And it's different for a lot of people. Like you're simulating all these work days and you're assuming perfection. So yeah.
And on the other hand, if the goal of this study is very clearly, also the author of the study owns it's Carl Zellick, right?
Yeah, so the first author of this paper has a lot of financial interest in the
So in
the company with the exoskeleton. So
in his world, he wants, thousands of people being able to wear this exoskeleton. And I do think there is a benefit, outside of, on a smaller research scale, to have some sort of metric that you can apply. Like think about BMI, right? Very imperfect, but for like very large scale, we may say like it correlates well enough. Could be nice to have a metric where like very large scale, again, you can kind of correlate some of these things. Andy, one of my questions is, it seems like it would have been not a huge burden for them to use some sort of like XSense or IMUs to kind of help time align some of their data and then also quantify some of that data out of the video.
yeah,
Why they didn't do that, or which was a different approach?
I definitely would have. Their main argument for using this assessment tool is that EMGs are expensive, they're hard to work with, like the data can be messy, you can have motion artifact, it takes a lot longer to process. So they want to create this visual tool.
Like OpenCap? Costing?
What's that? OpenCap?
Like OpenCap? Like a visual, like a,
Visual kinematic model.
yeah.
Yeah, like there's a lot of things that you could include. Like OpenCap, you just use like what, 2 or 3 phones, and you're able to kind of get a good estimate of what's happening. Yeah, so that's just like the major argument of this paper. They go into it a lot in the discussion section of how, you know, EMGs are expensive. Let's just use this tool. And then they try and defend it a lot with going into other studies where they've used back exos and they've said, oh, like their EMGs really haven't changed, like for their obliques or their,
They could have used a very basic IMU,
yeah,
sans EMG, right? Just an IMU is just, inertial measurement unit, right? Just tells you where it is in space. They could have put very basic IMUs on the passive exoskeleton, and they could have gotten a very rough estimate of things like trunk lean. So I'm kind of curious as to why in the article, did they defend that?
And in that case, they could
oh
have.
wait, they used the goniometer.
Yeah,
That's only for trunk to thigh angle.
yeah, but why not just have a IMU on these passive exos?
It's a good point. Yeah, I think it'd be a great improvement for the study. Yeah, Grace.
So in order to directly subtract the moments, don't they need to be in the same coordinate system and about the same joint?
Mhm.
Or-
Yes.
And like when I'm scrolling through this, I see some mention of how to kind of like transform. Do you understand how they transformed the back exoskeleton forces into a torque that's comparable to the first torque that they're
I'm not really sure because they don't go into it a lot.
oh, they can't just be measuring it like they did in Margaret's study.
Right. I'm
I
not.
think that makes it a terrible tool because everyone would be needing to do their own like modification to make it even like a fair subtraction. But I didn't.
Yeah.
Paper, sorry.
I haven't ever worn this before, so I'm not really sure like how it like works or like feels on your body.
They may also, because this is his company, I imagine he also has a database of said data that he could just go back and look at.
And
And
cheating.
Yeah.
Cool if we need Carl Zellick's database.
but then we have to buy his exoskeletons. Anyway,
Yeah.
it's a good point, Grace. It's not very helpful.
I like the idea of it, but it needs to be validated. Like, I wish they had done motion capture at least to validate this one-to-one subtraction.
Or just kinematics. They're not even motion capture.
Well, you need the force plates because you would need to calculate inverse dynamics and get the actual biological torque.
It's true, but I do think
And then
that-
it would be really cool if it does work out and it's a one-to-one
but
subtraction.
but that study has been done.
Not for this transformation though.
No,
Right.
but they have done not necessarily, but I think they've done enough that you could. I understand that their point was to have something that was more broader band.
Yeah.
Right.
Not great.
Yeah.
Get out of
Colin.
these videos. Oh, sorry.
Somebody else talk.
Or back accident or back injuries caused by long-term fatigue type stuff or more one-time accident type stuff?
I'm not really sure on like an exact number. But like this study is like based on like those long term. Like I've been lifting boxes 2,000 times like every work day. So it's like that buildup of like stress on your back over time that I think they're more concerned about. And they think like a back exo could like effectively help more with. What do you think?
If more accidents are caused by singular, like I did a lift incorrectly type
Yeah.
stuff, then this would be less helpful,
Mhm.
but maybe it could still do that because it's reducing fatigue.
I agree. Yeah. Yeah, so like I think that was another one of my questions here is like the heavy manual lifting. So I can't remember exactly the different size of boxes, but you think of people at the airports lifting like 60 to 100-pound bags or something like that could really result in like a singular like task that gives you a lot of strain on your back. That could be like a one-time injury, but they're also lifting like thousands of bags per day. So yeah.
Even,
Yeah.
even though the injury may happen in one instance, the mechanism, right? Like we know that when your muscles fatigue, they start to not do what we want them to do, and they start to have weird behavior. So, if you're reducing fatigue, maybe you're also reducing the opportunity for a single instance injury to occur, which I think is still valid, right? So even if you're not, if more people are getting injured not from long-term lifting, but just from these one-off cases, if these one-off cases are happening because people are fatigued, it may still be an effective tool.
Yeah, I would agree with that. Yeah.
I want to ask a little bit about the idea that the lead author on this has a financial stake in a company that sells exoskeletons. And I know it's not super uncommon in robotics. And
Yeah.
I was wondering how, and maybe up to the group as well, how do you how does that affect how you interpret a study or evaluate a study? It's interesting. I looked at the disclosure, and if you didn't know who Carl Zellick was, it's a very vague disclosure, which, again, it's not uncommon. But it's like, we really know, unless you know, how much of a financial interest he has in skeletons.
Yeah, like a couple of us, we've met him at conferences, so we know like who he is. But like there's definitely, I think, a want and a need to get this study out to like promote like his stuff so he can sell it to Toyota or Delta, whoever's gonna take it. So yeah, I think it's a big like confounding factor almost. Yeah.
And one thing when I worked for an exoskeleton company, this was like a thing that we would run into very often is that people want you to validate your technology, but you're usually in a kind of a new market or a new product. You're also the only one really qualified to validate your own technology. And so it creates something very interesting where you'll have companies, they'll write like white papers, right? Those aren't really like, those aren't like validated by peer reviewers or kind of a scientific article, but then also there aren't that very many people that can really quantify how good your device is or do this research. So I think it's really interesting because ideally, yeah, you don't want the person who's like has a financial interest to be doing the research, but also there's not many people that can do the research or are like qualified to really validate it. And I think it's a little bit of a problem in the field because also if you spin off one of these companies, you then can't really get funding to do your own research, right? You can't get funding from NIH or any sort of government source to do your own validation. So it's a little bit of a toxic circle. I'm not really sure how to get out of it, but I think it's interesting for sure.
For university partnerships, but I do have a former collaborator who has he's an engineer who started a startup company with a seat technology to reduce whole body vibration. There's an intellectual property concern too, that you don't want to share your invention with others, but you could be open with your data. So you could be open with the data. And then I think it's everyone's responsibility as peer reviewers and editors to ask the question, do you have conflicts of interest? And to disclose them. This same collaborator, I also had to say, no, you probably should disclose you own a company with a stake in seat technology, even though we weren't studying his seat, we were studying a seat. And it just, as peer reviewers, scholars, encouraging others to disclose can be helpful, but the editors probably didn't know or make the connection to push for a more thorough disclosure.
Yeah, maybe not. Yeah, it's hard to say, but yeah.
I have maybe weird question. I'm curious if anyone's looked at like observer bias in studies like this. So do people, when they know they're being taped or watched for a scientific study, end up doing things better than they would normally? Are they like not cutting corners versus, I don't know. Any thoughts you have on that kind of phenomenon?
I wouldn't say it's the best form. It's just a snapshot. He's kind of doing like this stooping like motion going to the side. So maybe this person didn't care as much. I don't know. But who's watching the video? Who's making those calculations? Who's saying, oh, this is the box is right here versus way out here that's going to create a much higher damage value, risk to injury value. Yeah, so there's a lot of bias within that kind of stuff, and this is just one person, so
Mhm.
um, yeah.
And then sort of have a follow-up question. I'm not familiar with, is there ever an event where this like video footage would be shared with like the leadership in a certain company, like showing like this is how your workers are currently moving and this is how the exoskeleton can help you? Because I would wonder if maybe employees were feeling like maybe Big Brothered a little bit if they were like being watched or they knew that that videotape was being shared with people that were making decisions and investing in these things.
Yeah.
If that makes sense.
Yeah, yeah, that makes sense. Yeah, it might have like some like psychological deal like with the workers
Yeah.
for sure. So, um, I'd also be curious to see like did they kind of train this guy at
Mhm.
all? Like what
Mhm.
was that? They didn't really go into how they trained the participant. So,
Yeah, absolutely.
yeah.
Thank you.
I think powered exoskeletons are sometimes used for minor workplace surveillance.
Yeah.
Because of the electronics on board, you can kind of see like, oh, how many lifts are people doing? So there are certain companies that like them for that more than maybe their intended purpose.
Interesting.